or creepy vans? Raise your hand. Whoever jumps at the chance.
I like dogs.
I like dog. Oh, I like gold. I like gold and money.
All right. So Patrick has one.
And
yeah.
move.
Max likes dogs. Jack likes gold.
Creepy vans.
Yeah, of course.
All right. Megan gets the creepy van.
Yes.
All right. Not yet. Well, actually, no. You might as well say stand in.
Megan, I'd like to remind you I'm a mandated reporter. Just sorry.
All right. Good to go.
Whenever you're ready.
All right, so my presentation is going to be based on chaos theory and physics. What would you think with the word chaos theory comes to your head? What would you normally think?
Disorder, random.
Yeah, disorder and random. Probably think something that looked like this. Yeah.
Oh, Matt. Oh, that was awesome.
All right. Shall we play a game?
Yes.
We have 4 volunteers here that want to play. The rest of the class are going to be observers of this very new game that you guys aren't very aware of, called Monopoly.
I'm so good at this game.
I beat Max once.
No, you're not. He was the banker.
So, sit down. Would you like to play?
Yes.
Yeah.
I am so happy I volunteered.
See who the rest of the volunteers we have. Dog. Max gets the dog. Jack gets the gold car.
Nice.
Oh,
yes, I get the money back.
You get the creepy van. I don't know if that's in the normal Monopoly, but I just found it, so we're rolling with it. Alright, so you guys are all on go. Now the goal of this, we are going to be focusing on player movement.
Isn't that gonna predict every single one of our moves or something?
Oh, we'll try to. Alright, so all of you guys are at what position are you guys at on the board?
Go.
Go. Which let's just change this board into a number line. Where would you guys consider yourself?
0.
Alright, so you guys are all at 0.
Negative 11.
Negative 11. I'm pretty sure that's not a space on the board, but and since I don't have dice, I'll just use a random number generator on my calculator to give you guys moves.
Matt, you're wonderful. No, I'm gold. Ladies first. Creepy van first.
It's gonna go in the order of dog, gold, money, creepy van.
Oh. Yes. There's the one with the treasure chest. Look at that.
All right. So we're starting at position 0, and Max goes and he rolls an 8. Moves ahead 8 spaces. So now what position are you at, Max?
8.
8. So Max moved ahead 8 positions and is therefore at position 8.
You can erase any of the rest of that stuff, Matt, by the way. Feel free to
All
get
right,
that out
I
of
don't need it for right now. All right, Jack, you rolled a 4.
Oh.
Yeah, you have to pay income tax, but
Where's our money?
for the purpose of this experiment, we're really only looking at the player movement. So what? So how many spaces do you move, Jack?
4.
And what position are you at?
4.
All right, Patrick,
Alright.
you rolled a 9.
That's because I'm the
So what position are you at right now?
I'm at position number 9.
Yeah. So do we all think that we have a firm grasp on Monopoly player movement right now?
Yeah, that's a plus sign. It's 0 plus 9 plus 9.
That should be an equal sign. Thank you for weighing that out.
Well, yes.
I think I understand
Yeah.
this.
Those are just basic position relationship.
Yeah.
All right, so you guys feel fairly confident until it's Megan's turn. Megan, you rolled a 7.
Oh, and this is complex right here.
Yeah. Are we gonna play out the
Oh,
move?
I'm gonna, okay.
Yeah.
Oh god.
Advance to St. Charles, please. If you pass, you'll collect $200.
Oh.
Oh, Matt planned this all out, didn't he?
So, what'd you roll, Megan?
7.
What position are you at?
11.
11.
That's tricky.
Why?
I like those bottom.
I thought we had a good grasp on player movement.
I thought we did too. I'm scared.
Well, luckily you guys are in good company because Newton made the same mistake that you did.
Okay.
Yeah.
Okay.
So
That's harsh. I don't call that a mistake. I call that a chance. Real form.
Did anyone get the War Games reference?
I did.
I did.
There we go. All right. When Newton was first finding the orbit of the moon and the Earth, he conveniently put the mass of the Earth and the mass of the moon into the equation, his universal law of gravitation. So F equals G m1, and well, I'll do mass of Earth, mass of moon, all over the radius squared. And when he put this in, he was trying to predict the orbit of the moon. And when he did this, he got very close to the correct answer. Until Kepler came along and he noticed that there were irregularities in the moon's orbit. Which means the moon was still orbiting around the Earth as expected, but certain times the moon would appear slightly farther or slightly further away from the Earth. And it wasn't until the 18th century when William Hill came along and he was like, you know what, there's this other massive object called the sun, and the sun also affects the movement of the moon around the Earth. So at first Newton thought that it was like a perfect system, that the moon was just moving around the Earth, until he looked at the data and found out, oh wait, there are actually other factors affecting the orbit of the moon, so I really can't predict it the best that I possibly did. Similar to the Monopoly game, where it seemed as if it was just similar movement, but really there were other spaces on the board such as chance, or the go to jail space, or you pick up advance to the nearest railroad. So the first step in understanding chaos here is understanding what a deterministic system is. And a deterministic system is a system that always produces the same output from a given starting condition or initial state. So like an equation such as y equals x squared, if you have the graph here, there's only, for every x, there's only like one possible y value that's going to come up. So let's take just here like a ball rolling down an inclined plane, or like water flowing down a hill. We'll just assume it's like frictionless and force of buoyancy is just negligible. That you can easily predict how after like 1 second how fast the ball will be moving and how much farther down the hill it is. But in a chaotic system, which was developed by Edward Lorenz, it essentially says that the initial conditions still determine the future, which is a deterministic system, but the approximate initial conditions do not determine the approximate future. So while that seems very wordy and stuff, it's essentially then like in this equation y equals x squared, if you were to have like a range of x values, so say between 2 and 3, you couldn't say that it's going to fall between 4 and 9. It could fall in this like much greater area because in this system the initial conditions are a lot more sensitive to the future. So let's say we were to take like the moon's orbit. Now because William Hill found out the sun, can we now accurately predict the orbit of the moon? No, why not? There are other planets. There's Mars, there's other stars, and there's tons of galaxies out there. So while it appears that, while it is true, the orbit of the moon is a deterministic system, the initial conditions of it do determine the future. The approximate initial conditions do not allow us to predict the future because we don't know if we can't get every single mass in the entire universe and find the force on the moon, or predict we don't know like a large mass might be moving towards the Earth at tons of meters per second, and in 1,000 years will suddenly drastically alter the course of the moon. So I decided to do another example, which is found in geography, called the coastline paradox. So let's say we were trying to estimate the coastline of Great Britain. Now, the way that cartographers would normally do it would be okay, we're going to move along at 500 meter intervals. So they take a satellite image and in this, or maybe not 500 meter, that's a little small, maybe 500 mile intervals. And say okay, there's that point, and then use a ruler and move 500 miles out onto Great Britain, and then every so on around, and then use that to estimate the coastline. And of course, you could easily get more and more precise, use, instead of 500 miles, maybe use 200 or 100, as you can see here. But it's impossible to actually find out the exact coastline because you just are unable to get that precise of a measurement, and the fact that the coastline is still changing due to the tides of the moon. So here, while people might think chaos is just random and just random things going around, The idea of chaos theory is that it is possible to predict it. It's just there are these really small variances that allow us to not be able to be perfect, such as the coastline of Great Britain. Which leads us to a very important question that we all have pondered in our lives, and many physicists and mathematicians have looked at. Can you predict the future of the universe? And according to chaos theory, yes, we can.
I like the asterisk.
Yeah, there's an asterisk though. Simply all we need to know is if you know the initial conditions and state of every particle in the universe.
Sweet. Let's get started on that.
So, if we were able to somehow categorize every single atom and molecule in the entire universe, every single location of them, where they started out, how fast they were moving in their current state, we would be able to successfully predict the universe. But according to chaos theory, because the only knowing the approximate positions or the approximate number of molecules, we are unable to approximately predict the future because there are just so many possible variables that could factor in, that could cause our future to be different. So, how is chaos theory actually useful in physics? If an observation is made and some of the data does not make sense or appears to have no pattern, is when chaos theory is normally used. So, essentially, with the orbit of the moon, if you see these little tiny variations or stuff, it's likely that there are just other small factors that can be used. So chaos theory isn't essentially saying, oh, it's just random, we can't predict it. It's essentially saying we can predict some of it, but the fact is that there are, in certain situations, so many factors that we cannot possibly control that it will appear that the result is chaotic, even though it's really in a deterministic system. So a lot of times, such as what William Hale did, you can research for underlying causes why this is true, but unfortunately it's not possible in some situations to accurately predict the future or the end result because we just don't simply have enough data. So that's really the difference between what chaos theory is and just a chaotic system or chaotic nature. Chaos theory really says that we can predict it if we had all the conditions, but unfortunately we won't be able to do that. So do we have any questions? No?
So when you're looking at a system that has an element of chaos to it, is it that there's a sort of a trailing end of complexity where you sort of give up, or is it pushing the boundaries of where you can gain predictability? That's the goal of the chaos theorists.
Yeah, the goal is to essentially gain more and more predictability. It's the fact that having knowledge of this, you can become more predictable. But the thing is that if you can't say that if you're getting I'm 90% the way there, therefore I'm going to be 90% correct in the future. Not knowing that other 10% can have drastic implications on the entire 100%. So while you can get closer and closer, actually what Edward Lorenz says is that in many situations, the fact that you don't know that other little percent, the fact that you do not know that little other percent means that the actual results of that other 90% cannot be predicted as accurately as one would expect.
So when handling a chaotic system, is part of it deciding kind of what your error bars are, like what kind of range of probability you have, and that gets sort of worse as you go outwards, or?
A chaos theory is actually not used in just a purely chaotic system because
Okay.
it's no idea. It's in more like a deterministic system, which essentially having the knowledge of this is means that wait, what was your question again?
When applying chaos theory, and perhaps forgive me if I'm referring to it as something other than what it is. Is the goal to create as good a model as possible and then try to come up with an understanding of how moving outward that model can become worse, or is that not something that's capable of handling?
Yeah, it's more like the idea of creating a model, but then seeing how accurate is that model actually, instead of saying oh, we're this percentage the way there, therefore we have this percentage done. It's more like creating that first model, then seeing, okay, how close is this model to the actual result we're going to get? and then saying like, okay, our margin of error due to like this chaos that is occurring is this like, a certain percentage, and then making the next model, seeing okay, how much closer are we actually getting then, like essentially like how much is our how theoretically close we are actually to how close we are in actual life. Is essentially how chaos theory is used.
Did you come across any good example applications?
Quantum mechanics
Okay.
is used frequently. Heisenberg uncertainty principle, the fact that no matter how much we know, like we can't know both position and speed. I forget the rate. And also the you can only like be 90% sure where a particle actually is. That's where it stems from. And while there's like more and more, like we're getting closer and closer, but a lot of it is just due to the fact that there are so many particles and so many things occurring that it's just we are unable to have the technology to predict the location and what's going to happen to every single particle there is. Patrick,
What's an example of a chaotic system?
chaotic system. At the quantum level, I guess, almost think light traveling through like the Higgs boson would be considered like chaotic because it's not like it's just like how light travels like very slowly, I believe, if I got that correct. That like light is traveling like very slowly through that medium. We can't like predict like, oh, light's going to move at this percentage of the speed of light. It's just like what's happening, like it just happens to be traveling at the difference. It's like perhaps that was a bad example. I can't think of a better one off the top of my head. But, at the quantum level, essentially. That's where this is used a lot, is at the quantum.
Is this the same kind of thing that's used in weather prediction to a certain extent, or is that sort of a different kind of chaos?
No, it's weather is one of the examples that they use. Of the fact that as they're fairly sure how like on the weather forecast according to everything to plan, but then suddenly it starts raining because weather's another. I was almost thinking of using weather instead of like the Monopoly game or Coast. I just thought the Monopoly game would be more fun.
Yeah, I like that.
Yeah, weather is a very common example where it's used. Yeah, definitely. That's like always listed.
Very cool.
That was beautiful.
Thank you, Patrick.